All right, in this video, I want to pick up where I left off in the last video where we talked about estimating the area underneath a curve using rectangles. Except here, I want to do some concrete examples. I want to actually calculate some values. We're going to start out with an example where we calculate L3. In order to do that, you need some formulas. The formulas might appear a little intimidating at first. I'm going to start you out with those formulas, but hopefully, based on what you learned in the previous video, you can make sense of those formulas. Here are the two formulas that you need. Okay, they look a little bit intimidating at first. They look really, really ugly. I promise you they're not that bad. First thing, if you haven't seen this before, this is what's called sigma notation. All this is telling you is you're going to add up a bunch of stuff. What do you mean a bunch of stuff? You're going to add up a bunch of copies of this. Whatever's to the right of this big Greek letter sigma is what you're going to add up. So we're going to add up a whole bunch of copies of delta x f of xi. Ooh, what do you mean add up a whole bunch of copies? We're going to have a separate copy for every single I from 0 to n minus 1. So the top and the bottom here tell you how many copies you're going to have by telling you what changes in each copy. And the only thing that changes in each copy is the letter I. So everything else is going to stay the exact same except for the letter I. And the letter I in the first copy is going to be a 0. Whatever's down here at the bottom is talking about the first copy. And in the last copy, it's going to be n minus 1. First copy, I is 0. Last copy, the I is n minus 1. So the way to think about this is telling me to take, let's see, my first copy would have a delta x times f of x. And then instead of writing the letter I, in my first copy, I want the I to be a 0. So f of x naught. That's it. And then I want to add to that my second copy. And my second copy will look a lot like my first copy, except I change the I. I add 1 to it. So instead of being 0, it's going to be a 1. Delta x, f of x1. Next one would be delta x, f of x2. And you'd keep going. You do this over and over and over again until you got to the last one. And the last one would be when I reach n minus 1. So it would be delta x, f of x. And then instead of writing the letter I, which went from 0 to 1 to 2 to 3 to 4, all the way up until it got to whatever n minus 1 were equal to. All right, n minus 1, how do I know what n minus 1 is? Well, in the problem, it's going to tell you what n is. All right, this is the formula for ln. For example, if I wanted you to calculate L3, you could use that formula, except in place of all the n's, you'd have a 3. So to check in to see if that made sense, if I have this memorized as the formula for ln, can I write the formula for L3? Well, let's see. L3 would be the sum, so there's my sigma notation, from I equals 0 all the way up to 2. Wait, why is it only going to 2? Because the value of n is 3, and it goes up to 1 less than whatever n is. So it goes from I equals 0 to 2 of delta x, f of xi. This is just saying add up a whole bunch of different copies of this thing. So the first copy I would have delta x, f of x0. The second copy I would have delta x, f of x1. And the third and last copy would be delta x, f of x2. Note that I end up adding together 3 things when I let I go from 0 to 2. That kind of makes sense. If I'm figuring out L3, I'm estimating the area underneath the curve with 3 rectangles. This is going to represent the first rectangle, this is going to represent the second rectangle, and this is going to represent the third rectangle. If I were using right endpoints, I'd have a different formula, but I don't want to overwhelm you with formulas right now. I'm going to save that for the next example. We're dealing with this formula up here, ln. L3 would look like this. It might help to have a picture. Here's what I'm interested in. Here's my curve, y equals x squared. Why y equals x squared? That was specified in the problem. I want the area underneath this curve from 1 to 7. Here's 1, here's 7. All right, here's a scaled version of this parabola. Maybe you can imagine it going over here. Anyways, I want to estimate this area in green. How am I going to estimate it? I'm going to draw rectangles. How many rectangles? 3 of them. All right, if I want to draw 3 rectangles, I need to divide up the area from 1 to 7 to make 3 rectangles. I need 4 points that are kind of equally spaced. What you'll see is they're at 1, 3, 5, and 7. I'll talk about how I figured that out in just a minute. And I'm going to call those points x0, x1, x2, and x3. All right, so x0 in this picture is 1, x1 in this picture is 3, x2 in this picture is 5, and x3 in this picture is 7. It's worth pointing out that A is also 1 and b is also 7 because a and b always correspond with x naught and x with the subscript of however many rectangles I'm using to estimate this area. So here's kind of the start of my picture. I want to draw rectangles using these points. The way I want to draw these rectangles is by figuring out their height based on their left endpoints. So my first rectangle that goes from 0 to 3 here, how tall should it be? Its height should be based on the height of the curve at x naught here, the height of the curve when x equals 1. The height of the second rectangle should be based on the height of the curve when x equals 3. Similarly, the height of the rectangle that goes from x1 to x2 should be based on the height at x1, and the height of the rectangle that goes from x2 to x3 should be based on the height at x2. That's why this rectangle only went up this high, didn't go up this high. What I want to do is I want to add up the areas of these three rectangles that you see pictured here. And each of these three terms will represent the area of each of these three rectangles. This term right here will represent the area of this first rectangle, and so on. And you might if you're really clever, be able to see how this mathematical mess represents the area of this first rectangle. Because think, what is the area of a rectangle? Well, it's the length of the base times the height. The length of the base, it appears to be 2 here, but it's really just the distance between x naught and x1, which is the same as the distance between x1 and x2, which is the same as the distance between x2 and x3. Oh, right, in the previous video, we gave those a name. That constant difference between any two consecutive x values is delta x. So this delta x right here is just talking about the distance from 1 to 3. It's just talking about the length of the base of the rectangle. So all I'm doing here is I have base here, and this is going to end up representing height. Base times height gives me the area of a rectangle. Wait, how does f of x0 represent the height? Well, the height of the rectangle is based on its left endpoint. The left endpoint is just f of this x value, right? F of 1 gives me the height of this curve when x equals 1. By putting the f of part in here, I'm getting the y coordinate, not the x coordinate. So all this is saying is the base of the first rectangle is delta x. The height of the first rectangle is f of x naught. The base of the second rectangle is delta x. The height of the second rectangle is f of x1. x1 is this value 3. The height when x equals 3 is this height right here, which ends up being 9, but we'll talk about that later. That's all I got to do. So let's see, delta x. You can just look at the picture and tell that it's 2, but I've been kind of trying to emphasize that we need formulas for this stuff. All right, we need formulas because eventually we're going to need expressions for this. We're not going to want numeric answers. So if you want an expression, how did I know that these were all 2 apart? How would you know those if you didn't have the picture? Well, delta x is always b minus a over n. All right, I guess I can memorize that for you if you want. I mean, you can, but you don't have to because it kind of makes sense, right? Delta x, b minus a, is talking about from 7 to 1. 7 minus 1 is 6. I have to cover a total area, a total length of 6. Yeah, how many rectangles are you going to build in that total length of 6? Well, I'm going to build 3 of them, whatever n is. N is 3 in this case. Okay, so if you have a length of 6 and 3 rectangles, how wide should each rectangle be? Well, 6 divided by 3. Right? B minus a over n, or in this case, 7 minus 1 divided by 3, gives me the constant width, the constant length of the base of these different rectangles. Okay, well that's almost enough information for me to figure everything out. I now know that these delta x's will all be 2's, 7 minus 1 over 3. If I could just figure out what these different x values were, then I could plug them into my function, y equals x squared, to get f of those different x values. So I kind of need to know what x0 is, what x1 is, and what x2 is. And well, in this case, we have a picture that we can just kind of look at. x0 was 1, x1 was 3, and x2 was 5. That's easy enough. Right, but what if you don't have a picture? What if you want to do this more symbolically? Well, x0 is always just equal to a. X0 is always equal to a, and a is going to be given to us in the problem. Okay, that's kind of nice, but what about x1 and x2? Well, x1, this 3 right here, the way you could think about this value being 3 is it's not quite a. It's a after you add one of these delta x's. Right? It's a plus 1 of these delta x's. Similarly, this 5 is just a plus 2 of these delta x's. In fact, if I wanted a general formula for what xi were equal to for any value I, 1, 2, 3, whatever you want, I could just say it's whatever a is plus some number I of them, delta x's. So in this case, I don't really have to worry about it, but imagine if you had 30 rectangles and you wanted to know what x27 was. X with a little 27 in the subscript. Well, all you'd have to do is start with A and then add 27 of these delta x's. Well, how big is delta x? I got a formula for that. Right? So I keep adding to my list up here in red of formulas, things you should have memorized. But I kind of argue that it's less memorization and more understanding. These can become intuitive if you talk yourself into them, and then it's a lot less memorization. And the other good piece of news is we're done at this point. The only formulas I need you to have memorized are the things in boxes. And I'd argue that it's really just two formulas, a formula for using left endpoints and a formula for using right endpoints. But if you look at those formulas, they have weird things in them like delta x's and xi's. And so in order to be able to put in the right things for delta x and xi, you kind of need this last box down here. Back to our example. I think we can now answer this question. We were asked to estimate the area under this curve by calculating L3. And to be perfectly honest with you, it's a lot easier to calculate L3 by kind of drawing the picture and being like, this first rectangle has a height of 1 and a base of 2, so its area is 2. And this rectangle has a height of 9 and a base of 2, so its area is 18. And this rectangle has a height of 25 and a base of 2, so its area is 50. I think I did all those calculations right in my head. It's easier to get the answer that way, but that won't serve you well in the next section. The way you'll have to be able to answer this to be successful in the next section is using this formula. It tells you that if you want to estimate the area by calculating 3 rectangles using left endpoints, here's your formula. And it looks overwhelming, it looks really scary, but maybe you're starting to believe me that these formulas are a little bit more intuitive than they look if you can understand these different pieces. So in this case, we first change this messy looking formula into the sum of these 3 terms. Be good if you get from here to here. Because from here going forward, all we need to know are what delta x are and what x naught, x1, and x2 are. Delta x is a constant, it's just the number 2. So this is equal to 2 times f of x naught plus 2f of x1 plus 2f of x2. I'm just changing the delta x's into 2's. What are x naught, x1, and x2? Well, I enumerated those here. They're 1, 3, and 5. More generally, they're a plus 1 of these delta x's, and a plus 2 of these delta x's. Because for any x with the subscript in there, I can figure out what it's equal to with this formula. Plugging in for x naught, x1, and x2, 1, 3, and 5, gives me this expression. F of 1 is just asking me what comes out of this function when I put 1 in. Well, since my function is y equals x squared, when I put a 1 in, 1 squared is just 1. This is just 2 times 1. What about when I put 3 into the function? What would come out would be 9 because 3 squared is 9. This is just 2 times 9. What about here? If I put 5 in, well, 5 squared is 25. So I'd get 2 times 25. I got 2 plus 18 plus 50. If I add up those 3 numbers, I get 70. It's easy to get lost in the algebra down here, and it's even advantageous to be able to get lost in the algebra, but it would be nice if you could tie that back to this picture. This 2 is the area of this rectangle. This 18 is the area of this rectangle. This 50 is the area of this rectangle. Why? Because this rectangle right here, its area is its base times its height. Its base is 2, and its height is 25. Why? Because the height of this curve, when x equals 5, is 25. This height right here is 25. Let's do that one more time, but a little bit quicker. Suppose you were asked to estimate the area under this same curve, y equals x squared. Again, from 1 to 7, sometimes the x values are specified as x equals 1 and x equals 7. Sometimes it's just implied when they say 1 to 7. Of course, they're talking about the x value. By calculating R2, 2 things have changed. It's no longer left endpoints that I'm using to determine the height of the rectangles. They're right endpoints. The other thing that changed is I'm no longer having 3 rectangles. I'm now only having 2 rectangles. No problem. I take my area from 1 to 7, and I want to divide that up so that I have 2 rectangles. In order to create 2 rectangles, what I need are 3 points. The first point is going to be at A. The third point, the last point, is going to be at B. And then I need one more. It'll end up being right in the middle in order to have these equally spaced out. All right, don't follow that. That's okay. We have a formula for that. And I want to create rectangles. So I want to create two rectangles, one from here to here, one from here to here, and I want the height of this first rectangle to be determined by that height right there. Whatever this height is the height of that rectangle. And I want the height of my second rectangle to be determined by this point way up here. Whatever this height is right here, its right endpoint determines the height of this rectangle. The sum of the area of this rectangle and this rectangle is what R2 is defined to be. I have a formula for R2, or a general formula for Rn. It looks a lot like the formula for Ln. It's still the sum of a bunch of different terms. And each term itself is the area of a rectangle. And the area of the rectangles are still the width of the rectangle times the height of the rectangle, just like they were up here. It's just you see that the start and the end changes a little bit. And that kind of makes sense, right? The height of the first rectangle, when I'm using left endpoints, is x naught, right? It's the height at x naught. It's f of x naught. Going back to this picture, the height of my first rectangle, if I'm using left endpoints, is based on the height at x naught. The height of my first rectangle, if I'm using right endpoints, is the height at x1. So when I look at the formula for Rn as opposed to Ln, I don't want my first term to base the height on x naught. I don't want I to be equal to 0. I want my first term to base the height on x1. I want to start out when I equals 1. Instead of stopping 1 less than n, I'm going to stop at n, because for the last rectangle here, I want the height to be based upon, in this picture, x4, right? It's right endpoint. Whereas in this picture where I had left endpoints, the height wasn't based on this last x value, x3 in this case. It was based on x2, so I stopped 1 short. But in my last rectangle with right endpoints, I want to base the height upon x with the last subscript. So that's why this goes from 1 to n. It'd be nice if you could look at this sigma notation and you understood that this was just saying delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3. And you keep going until you get to f of xn. Unlike up here where we stopped at n minus 1, down here we stop at n. So what I'm saying in this specific example where I'm asked to calculate R2, well, I have a formula for R2. Essentially what I'm going to do is I'm going to copy this formula, except I'm going to change all the n's into 2. So I'm going to want the sum from I equals 1 up to 2. Right, just changing this n into a 2 of delta x f of xi. That's my formula for R2. In order to use this formula, I need to know what delta x is, and I need to know what all the different xi's are. You can get that from the picture, or you can get that more algebraically. Delta x is always b minus a over n. B is still 7, a is still 1, but be careful, now n is equal to 2 because we were specified it was R2. This has nothing to do with changing from left to right endpoints. It has to do with my subscript changing from 3 to 2. The subscript always tells you the value of n. 6 minus 2 is 3. If I wanted to enumerate a bunch of x values, I could figure out x0 and x1 and x2. I could figure out these different x values in my picture. x0 is always just equal to a. A is specified in the problem to be 1. x1 is not quite a. It's a lot like a, but you got to add 1 of these delta x's. So it's 1 plus 3 more. In other words, 4. And x2 is kind of like a, but you have to add 2 of these delta x's. So it's 1 plus 2 of these 3's. It's 1 plus 6. It's 7. Same way I got them before. X for any I is always a plus I delta x. Right, this was just a plus 0 of these delta x's. This was a plus 1 of these delta x's. This was a plus 2 of these delta x's. X naught, x1, and x2 are 1, 4, and 7. Although what you'll see when you expand this sum is that you really only care about x1 and x2. When I'm making these rectangles right here, I don't even care about the height at x naught. Because I'm using right endpoints, I only care about x1 and x2. I'm going to expand this sigma notation by copying what's written right here over and over again, changing only the value of I. And I'm going to start letting that value of I be 1, and I'm going to continue to write copies of it until my I gets all the way up to, well, just 2 in this case. So it's delta x f of x1, right? My I is a 1. Delta x f of x2, and I would continue x3, x4, x5 all the way until I get to whatever number's up here. In this case, it's just 2, so I stop right here. You only have two terms? That doesn't seem right. Yeah, you only have two terms because you only have two rectangles. Because I'm calculating R2, there's only two rectangles whose area I need to add up to estimate the area. Delta x, we already figured out that that was equal to 3. F of x1 is just asking me f of 4. And then for the second term, delta x is still 3. F of x2 is just asking me for f of 7. Because f of x here is y equals x squared, to get the output of these functions, I just square them. So 3 times 16 gives me the area of the first rectangle. 3 times 49 gives me the area of the second rectangle. Note, this could be a different function. This could be e to the x power. And then this would be e to the fourth and e to the seventh. Right, it's whatever comes out of this function when you put the specified values of x in. Now I just go through and I add up and multiply some numbers. 3 times 16 is 48. 3 times 49 is 147, I think. And 147 plus 48 is 195, I think. But really, I don't even care so much about the numbers. You could have gotten the numbers a lot easier just from looking at the pictures. What I want you to get out of these is understanding these formulas. These formulas have to make sense. You have to be able to deal with this sigma notation and understand delta x and these xi ideas. And I think the easiest way to understanding them is by tying them back to these pictures. And to test if you understand them, we'll see if you can come up with these numbers, like the number 70 and the number 195. But really, the purpose of learning all this is not to come up with the numbers, it's to be able to later manipulate these expressions.